Hello, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RVCCPS IASC. It's my pleasure to introduce today's speaker, Dr. Praneeth Netrapalli. He will be speaking on efficient LLM interference with HiRE and Tandem transformers. Praneeth Netrapalli is a research scientist at Google Research India, Bangalore. He is also an adjunct professor at C-Mines, IIT Bombay, and TIFR Mumbai, and a faculty associate of ICTS Bangalore. Prior to this, he was a researcher at Microsoft Research. He obtained MS and PhD in ECE from UT Austin and BTech in EE from IIT Bombay. He is also a co-recipient of IEEE Signal Processing Society Best Paper Award 2019, Indian National Science Academy Medal for Young Scientists 2021, and was an associate of Indian Academy of Sciences 2019 to 2020. His current research interests are broadly around improving efficiency and capabilities of LLM. Over to you.
Thank you. Thank you, Srishma. And thanks to the organizers for inviting me. And thank you all for coming. So today I'll be talking about inference efficient LLMs, and this is based on joint work with like a number of wonderful colleagues from Google. At any point of the during the talk, if there are any questions, feel free to raise your hands. So in case I need to write something, I'll write here. Hopefully that's visible to everyone. Okay. Okay. So because I specifically mentioned like inference efficiency, let me first talk about training efficiency and inference efficiency. So, as you might be familiar with, like any model during its life cycle usually has like two phases. One is the training phase where the model is actually trained, and the second phase is inference or deployment after training, where you deploy it for people to use it, right? And so both of them turn out to be fairly different in terms of like the kind of operations that they perform during training versus during inference. And so you can talk about both training efficiency as well as inference efficiency. The main reason motivating inference efficiency in particular is that training is usually a one-time cost. So you train the model and then you usually keep it. And however, like inference is a continuous cost. So as long as the model is being used, people keep sending queries or inputs, and then the model needs to process them and generate an output, right? And there are studies which suggest that over the life cycle of a model, the overall cost or say and like the resultant carbon emissions and so on of over the entire life cycle of a model, out of that about 80% is comes up during inference and not and only the remaining 20% comes up during training, right? So inference efficiency is pretty important because of the overall because it dominates the overall cost of a model during its entire lifetime. And also the high inference cost of these models is also a important hurdle in being able to deploy the most powerful models. For example, if you know of like O1, O3, or some of these reasoning style models or DeepSeek R1 and so on. So they are extremely expensive during inference time because like they generate very long chains of thoughts. The output length is very long, and because of that, they're very expensive to serve. So that's the reason like they're priced extremely highly and have been released only in like a limited fashion. So improving the inference cost of these LLM deployments is also crucial in enabling these models to be more usable by a wider range at a lower cost compared to whatever they're currently being deployed at. And because of all of these reasons, inference efficiency is a very active area of research, and it does span several different areas, including algorithms, architectures, meaning like the transformer architectures and modifications to transformer architectures and things like that. And again, like systems, hardware, and yeah, so it's a pretty active research area spanning like many different areas. Yeah. So I had to share this on Zoom, and that's why it is like this. Yeah. Yeah. I think because of Zoom sharing, I think like this is probably the maximum size it can come to. Okay. Okay. So before we go into more technical details, let me try to first explain at a high level what are the important components of a transformer. And transformer, because like all these LLM, like the big LLMs are basically transformer models, and they're autoregressive as well. So we'll come to what autoregressive nature is in the next slide. But let me first start with what a transformer is and what are the main blocks of a transformer. So transformer basically is a sequence to sequence model, which means that it takes a sequence and then it outputs a sequence as well. So it might take a query and then it might output a response. So a query will be, let's say, a sentence, and a sentence can be thought of as a sequence of words or tokens, right? Yeah. So tokens is basically, we can think of it morally as being equivalent to a word or maybe subword and so on. So there are different kinds of tokenizers, but roughly we can think of each token to be roughly corresponding to a word. So the input is going to be a sequence of words or tokens, and then the transformer basically converts this into an output, which is again a sequence of words or tokens, right? And there are three important components of a transformer. So the first one is the embedding or softmax layer. What this does is embeddings at the input, it takes a word or a token, and then which is a discrete ID. It's saying so we have an entire dictionary of all possible words, and for each word we give a particular ID. So the word number 1 is A, the word number 2 is the, and so on, right? So we take a particular word ID and then we assign a continuous vector to it. So that's called this embedding or embedding table. And this is again applied independently to each token. So we just look at the word ID and then we look at the corresponding vector that's assigned to that particular. So all of these parameters will be learnable. Like what is the vector associated to this particular word will be something that the model will learn during training, right? So that's the embedding layer. Then we have the feed forward layer, which basically takes in a vector x and then applies this transformation, which is w2 times phi of w1 times x. So x is a vector, w1 will be a matrix. Phi here is a nonlinearity, which is applied element wise. So for example, like the ReLU nonlinearity will be just of max of 0 comma a, and then we'll get another vector here. So w1x was a vector, phi of w1x is another vector, and then we multiply by w2, right? So this is what is called the feed forward layer, and w2 and w1 will be the learnable parameters here, right? So we had a input ID which was converted into a vector by this embedding layer, and then that vector could be passed into a feed forward layer, which again outputs another vector, which is ffw of x. And then the most important innovation in the transformer is what is called the attention layer. And what the main thing that distinguishes attention layer from the remaining two is the following, that both of these are applied independently to each token or each token ID, right? So we have a vector and then we are converting this into another vector. Similarly, here we have an ID and then we are just using it to represent another vector, right? Whereas what attention layer does is it couples all the different tokens that are appearing in the given sequence, right? So what does attention layer do? Okay. So let's say we are given the input token or embeddings of like the sequence of tokens that we have, say they're represented by x1 to xn. So each xi is a vector. The attention layer basically has three different parameters. So one is called the query matrix, which is represented by q. K is the key matrix and v is the value matrix. So we have these three different matrices, q, k, and v. And for each of the input token vectors, xi, we compute the query, key, and value vectors. So each token.
But one query has n tokens.
Yeah, one query has n tokens, and each token is being processed this way. Yeah, and attention basically tries to kind of make sense out of that sequence of tokens as a whole. And yeah, this is for one particular token. We have a query, we have a key, and we have a value vector. They're represented by qi, ki, and vi. And the attention layer takes in all of these xis and it gives an output which is like so there will be an output corresponding to each of the tokens. So x1, x2 up all the way up to xn are the inputs. So we have n inputs, and then it will give output corresponding to each of them. Let's call them x twiddle I, x twiddle 1, x twiddle 2, all the way up to x twiddle n. And what the attention layer does is it comes. So for xi, if we look at the causal variant where a xi looks at only all the tokens that have come before it, so it only depends on x1 to xi. It takes a weighted combination Pij of all the different value vectors Vj, right? And these probabilities Pij are computed using the query of the current token Qi and the key of the jth token Kj, right? So Pij is just proportional to exponential of Qi inner product Kj, and Z is a normalization factor, which is chosen so that like the summation over Pij, where we sum over j is equal to 1. So there's a probability distribution, and then we are taking a weighted combination of these value vectors Vj, right? So this is the output of Xi, and the main thing to note about this one compared to like the feed forward and embedding layers is that this combines all the information from X1 to Xi and then transforms Xi in this way. And this is where like the contextual information about like what are all the other tokens in the query doing and what meaning do they give to the current token happen. Okay. Yeah, and there are like multiple variants or aspects of this, which is like how many heads do we have. So this can be thought of as a single attention head. We can take multiple attention heads and then take a linear combination over them or some other matrix multiplication with it. And again, like this is a causal variant where X really depends on J for J less than or equal to pi. Where we can also think of bidirectional attention where J can go from 1 to n. So Xi not only depends on the previous tokens, but also all the tokens in the sequence. Right?
If I have a sequence like this is a cat, then the word cat will attend to itself the highest rather than attending it to other words. Is it like that or?
Yeah, empirically it turns out to be.
So does it help? Because if the word is attending to itself the maximum number of times, then are we going to have a good amount of attention of that word with other words in the sequence?
So is your question whether it makes sense to have J not equal to I here and whether that would work better or?
Yeah, so basically the question is if I have let's say 5 words in a given sequence, then the attention of that word with itself will be always maximum, right? Or no?
It need not be maximum. I mean, we are using different matrices Q and K here, right? So even if you take like Xi and Xi here, if Q and K were identity, then like Xi would probably be the have maximum inner product with itself because like both of them will be aligned. But because you have a Q matrix multiplying Xi and then a K matrix multiplying this, even for the same Xi, Q could like K could rotate in a different way compared to Q. So it's not required that they have. Yeah, so let me, okay. So this is the attention mechanism. So let me come to the next part, how a transformer is like fully built in this way. So an example transformer layer would be something like this, where we have an input. So there will be an embedding layer here, which actually, so firstly, there will be a tokenizer, which says how to break this down into like smaller tokens. So then you'll represent this as a sequence of tokens. Then you will have an embedding layer, which converts these sequence of tokens, which is sequence of IDs, into sequence of vectors in some dimension. And then each transformer layer consists of an attention layer and a feed forward layer. And then you can repeat it a number of times. Say if the depth is 10, then you will repeat it 10 times. And I did not represent it here, but usually you also have residual connections so that gradients flow backwards and the learning. So residual connections is important for deeper networks to be trained properly. Otherwise, we saturate at a very high loss without residual connection. Anyway, so yeah, so each attention, a combination of attention layer and a feed forward layer is called a transformer layer, and we can have like a deep transformer which basically replicates a combination of attention and feed forward multiple times. At the end, we have a softmax layers, which usually just uses the same vectors as the embedding. But what the softmax does is that we have an output representation for each of the tokens, right? And the softmax layer multiplies the embedding for each token with this particular representation, and then takes a softmax to give a probability distribution over what the next token could be, right? So that's the softmax layer. But in terms of parameters, like the softmax and the embedding layers are usually identical.
So what is that feed forward layer doing exactly in this target?
I mean, mathematically,
like is it like giving more weightage to a particular attention vector, or what exactly it is doing?
Conceptually, you mean?
Conceptually.
Conceptually, we can think of it as some kind of hard-coded memory bank or a retriever, where, so for example, we have this equation for, so W2 times phi of W1x, right? So if we think of x as a vector, so if we think of W1s as a nearest neighbor index, W1 and W2 as nearest neighbor index, right? So W1 times x is telling you which of the rows are going to be closest to x. So they will have the largest magnitude. And then when you multiply it with W2, you will basically pick only those particular columns of W2. So we can think of this as doing some kind of parametric nearest neighbors, where you are encoding like keys and values in this parametric space. So in the attention layer, its keys and values are coming from all of the past tokens. Here, like these W1 and W2, we can again think of these as similar to attention layer, but this is a parametric attention layer where W1 is like the key vector. Given a x, you are multiplying with this key vectors and then identifying which are the top ones, and then W2 will give you the corresponding values. So you're not explicitly doing a probability distribution and so on, but intuitively it seems like this is playing the role of identifying the nearest neighbor and then using that value to update its vector. Yeah. Okay. So so far we have seen what a transformer consists of, which is basically these attention, feed forward, and embedding softmax layers. And when we give a input or query to the model, let's say what are Himalayas, then the model, what it does is it it is autoregressive. What it means is that it generates only one token at a time. So with this prefix, it outputs the first response token, like it only predicts the next token. So that will be, let's say, Himalayas, and only after we see what this token is, we'll be able to give it as an input, and then it will produce the next token, which is maybe R, and then we again give it as an input, uh, and then it eventually gives an output, right? So the point I want to highlight here is that this is fully autoregressive, meaning that we can only generate this only one token at a time, because in order to generate like the second output token, you need the first output token as an input, and which means that you first need to generate the first output token before you can pass it as an input. So you do all of this computation through attention layer, feed forward layer, and softmax to compute the first output token. Then you take this first output token and then you pass it as an input, and then you produce the second output token, and then yeah, uh, yeah. Yeah, that's a good point. So usually, as we said, like feed forward and softmax don't have any dependence with what has come in the past. It's only the attention layer which couples the computation that has to happen here with what happened in the past. And if we see the exact way that attention has this dependence is through these keys and values, right? So for a given I, all you need to store is kj and bj for j less than or equal to I. So what you usually do is in these attention layers, you store the keys and values for these attention layers corresponding to this prefix. So you don't need to reprocess all of this. You just store the keys and values corresponding to each of these tokens here in each of the attention layers. And whenever you are processing this token, you use all those keys and values in each of the tokens to do that computation. Yeah. And then you sample. So it will be a distribution. You just pick a sample, and that's also important for producing a valid sentence, because there could be multiple different sentences that you could use as a response to what are Himalayas, for example, right? The first one could, like one sentence could be Himalayas are mountain. The other could start with the Himalayas, for example, right? And the second token really depends on what you had sampled to be the first token. If my first token ended up being then the second token could have been Himalayas, for example, right? But if I sampled the first token to be Himalayas, the second one cannot be Himalayas. It doesn't make sense, right? So like the sampling step is also important, like is an important constraint which actually forces this to be autoregressive. Yeah.
So the output sequence number of words is variable. You never know how many words are the ChatGPT may be giving you.
Yeah.
So the size of the attention matrix itself is variable, because each and every word that is outputted by ChatGPT.
Yeah.
Now you have to take the attention with your question, the words in the question, So how do you make sure like even if the ChatGPT gives you a long amount of output, I will be able to still store it appropriately because it seems the size itself is very.
Usually you have like a maximum length, and like I don't know what exactly it's for ChatGPT, but I would think it will be on the order of like
More than 48 hours.
yeah, I mean public version, but I think like internally or for paid versions they could even have like 128,000 output length and so on. Certainly like the thinking models output like much longer generations. So usually have the maximum output length which will be fixed. But then like some of the efficiency approaches there could be, if you are producing the first few tokens, you should not be spending the same amount of time and attention as you would be spending in the very last tokens, because you have fewer things to attend to, right?
But again, the
So
problem will be if you fix the amount of memory and if the output that ChatGPT gives is very small, then you are wasting that memory.
again, like there are approaches, like you can look up this approach called page retention, for example. So there are ways to make this more efficient, so that even when you set like a maximum sequence length, if the actual output turns out to be much smaller than the maximum length, you don't want to spend this like compute resources or time or memory that corresponds to the maximum. You only want to spend whatever you are actually spending. So your page retention is one such approach. Yeah. Actually, I'll come to that in the next slide. Okay, so I'll come in a bit, but basically all of them can be expensive depending on the setting. So it depends on the model size, it depends on the sequence length, and it depends on uh, yeah, maybe model size and sequence length. Like these are the two main axes, and in some cases, like for long sequence length, for example, attention could be the bottleneck, and for large models but shorter sequence length, feed forward, and for small models and relatively small sequence length, even softmax can be a bottleneck. Okay, so we just saw like how these models generate tokens autoregressively, and the first thing I want to convince you about is that autoregressive generation is a real bottleneck in being able to effectively use the hardware that these models are usually deployed on. You might know that like machine learning, most of the machine learning workloads use like machine learning accelerators like GPUs and TPUs. And the main benefit of these GPUs and TPUs is that they are optimized for matrix multiplication. So you have a like you have large matrices that you want to multiply. GPUs and TPUs are optimized to do these computations like very effectively. And one way to think about this is that matrix vector like on these devices, matrix vector multiplication takes similar time as matrix multiplication, right? So even if you are doing matrix vector multiplication, which will have like fewer number of flops, because you have a matrix and you only need to like the number of flops is linear in the matrix size, for example. Whereas in matrix multiplication, it could be 1.5, like number of parameters in the matrix to the 1.5 if they are square matrices, for example. But the matrix, but on GPUs and TPUs, because of the way their hardware is structured, matrix vector multiplications take similar time as matrix multiplication, right? And if you look at what happens during autoregressive generation, say let's say in the feed forward network, we have only one input that's being given to us. So when we are doing W2 times P of W1x, we just have matrix vector multiplication. So W1x is a matrix vector multiplication, and similarly W2 times the C of W1x is again another matrix vector multiplication. Similarly, even when we are computing this attention, if we have only one vector, one token that we are trying to compute the attention output for, then we again need to evaluate these probabilities, which in turn require us to evaluate this Qi times Kj for all the different Js, right? That's again a matrix vector multiplication. So what this suggests is that this really cannot exploit the maximum flops or compute that the GPUs and TPUs are capable of, because we are mostly we are not able to make use of these matrix multiplications, and are essentially stuck with like doing sequential matrix vector multiplications. Yeah. I guess it just depends on the architecture of these GPUs or TPUs. Like they have registers which are shaped in the form of a matrix. So one matrix is loaded into like one of the registers, and the other registers basically send the vectors in a I don't know if I'll be able to explain it well, but if you have like a product of EB, so you have a register which is say 8 cross 8 matrix multiplication or 32 cross 32. So you load like a 8 cross 8 chunk here, and then you keep something like, so you send B1 and then B2 with null token, null element, B3 with something like this. So each of these basically does a multiplication. So this will have say A11, A12 like this. Right. So each of these basically does a multiplication of the element that it's currently getting, and then passes the accumulated thing below. And this is how it is structured. So even if you have a single vector, you are essentially, I think maybe your vector will be passed something like this, right? So you'll pass it here, then this will multiply, and then this will send it down. And at the same time, the second element would have come here, it'll add, and then it'll send it down. So you are wasting, so you'll have a lot of padding here essentially.
Doesn't it make sense to make the architecture which is optimized for vector matrix multiplication rather than doing matrix multiplication? Because if most of the what you can say the operations are focused on the matrix vector multiplication, then it would be much better to design the hardware like that.
Yeah. So again, like hardware cycles are usually at least 3 years, or like from design to actually getting something out. That's the first thing. But GPUs, TPUs are very effective during training. So the primary issue here is because of autoregressive generation. There are like the GPUs and TPUs were designed for workloads which were not necessarily autoregressive generation. For example, like during training, GPUs and like the matrix multiplication units are very effective. And at the same time, we will come a little later. Changing hardware is always like a harder proposition compared to changing algorithms. So there are certainly like more effective algorithms which are able to do like utilize these GPUs and TPUs more effectively as well. So maybe we'll look at some of these. No, but you can pass like the entire sequence all at once. So you don't have to do autoregressive training, because like you have the entire training data. So yeah, you just use like some kind of masking to okay. Yeah, and yeah, so this is very specific to autoregressive inference. And part of the talk will be about how to make use of matrix multiplication more effectively during autoregressive generation. And another part would be, because matrix multiplication, like the computation is not the bottleneck here, because we could have potentially done like many more flops compared to whatever we are doing. What is the bottleneck, and then can we reduce that particular bottleneck? Yeah. So yeah, so I'll try to talk about two approaches. So the first one is called HiRE, and the second one is called tandem transformers. So in HiRE, let's say we are doing autoregressive generation. What we want to do is that the number of computations that we are doing is no longer the bottleneck, and it turns out that the amount of time taken for transferring the model weights or the data from across different hierarchies of memory. So in a computer, usually we have a RAM, and then we have a cache, and like different hierarchies of memory, right? The faster memories are smaller in size, and the slower ones are where we will be able to put in most of the data that we have. So if we can somehow minimize the total amount of data transfer that we need to do, it turns out that because that's the bottleneck in autoregressive generation, we'll be able to speed up inference in terms of latency. Yeah, so let me explain this in a bit more detail when we go into the HiRE method. The second approach is what is called tandem transformers, and the main idea here is if we can mitigate the autoregressive nature of LLMs. And the high level idea about tandem transformers is that we want to use a small language model in this autoregressive mode, and a large language model which is augmented with it, to run in a block mode. So we generate maybe 5 tokens autoregressively using the small model. Then the large model processes these 5 tokens in a block mode, in a batch, and updates the keys and values for those tokens. And anyway, like those are the only things that we need for generating any future tokens. And this can hopefully combine the benefits of the small language model in autoregressive mode because it's smaller. At the same time, the quality can be boosted by using this large language model in a block mode. So let me try to cover both of these in a bit more detail over the next few slides. So the first part is HiRE. So referring back to one of the questions earlier, so it turns out that depending on the model size and the sequence length and so on, like different layers, like attention is in red, feedforward is in blue, and softmax is in green. So different layers could contribute to different amounts of latency. So it does depend on like the settings, and also like what's the batch size you're using and so on. The point I want to make here is that while the contributor to overall latency could be different layers in different settings, it turns out that in all of these cases, the underlying reason for the high latency in all these different layers turns out to be the transfer of model weights or KV cache from HBM to VMEM, or we can call it maybe RAM to cache. So the architecture will be something like this. So we have this high bandwidth memory, and then we have a smaller thing which is say cache, right? So this is relatively slow, and then we will have a processor or matrix multiplication unit, right? So this will be large. This will be in say tens of GBs, let's say, and this will be only hundreds of MB. And if you have a model which is very large, for example, like the DeepSeek models are on the order of like 100 billion parameter models. So even after quantization and so on, so you would need at least about 50 to 100 GB of space to actually store that model, right? And let's say you even store it on 2 different machines by partitioning model weights on different each of them. And so let's say about 50 GB of model weights. And you'll again have KV cache, which is for all the tokens that you have processed so far. You will compute keys and values in the attention layers. You still have to store them in order to be able to do the attention computation for all the future tokens, right? So the KV cache, again, maybe this depends on batch size, but let's say like 2 to 3 GB of KV cache. So neither of these will fit in this cache, right? And whenever you want to do a feed-forward computation in the processor, in the matrix multiplication unit, you need the corresponding model weights to be fetched from HBM. So because of the size of this, you cannot fit them in the cache. You can only fit them in HBM, right? And whenever you want to use it for any computation, you have to fetch it from here. And what we are saying is that this HBM, like fetching weight from HBM is much slower compared to fetching from the cache, right? So what we want to do is that instead of having to fetch the entire weights, if we can somehow look at the sparsity patterns in the model and identify that only some of the parameters are required for me to do the computation effectively, then we will only fetch like a smaller number of parameters, which reduces the overall time taken to fetch the parameters, and this reduces the overall latency. Does it make sense? Any questions? Yeah.
They are not showing queries. Is it just called KV cache? They are not showing queries there.
Queries themselves, I mean, we'll process them and then we will not store them. Yeah.
And these model weights are like, these are the weights that are there in the
feed-forward network, and then attention has these QKV matrices, and then softmax is also like a large matrix.
So KV matrices are stored in the KV cache.
So KV, there is a parameter which takes in xi, and then you multiply it, and then you get kj and vj. So the kj and vj are what is part of KV cache. That depends on the input. The k matrix, v matrix are part of the model. So those are the model weights. Yeah, so let me come to that. At this point, I just wanted to highlight what exactly is HBM and VMEM, and what is the bottleneck, which is this transfer, and how we hope to reduce it. I'll come to how we do it in the next few slides. Okay.
And is this the reason, like when your input sequence, the number of words in the input sequence increase, the size of the KV cache increase, and that's why your the most of the latency is coming from the attention?
Exactly. Yeah.
That is the reason.
Yeah, that's the reason. Yeah.
The sequence length increases, it seems like the attention is the one which is getting utilized.
Yeah. Yeah. For very long sequence length, yes.
So you're saying that so even though you still the model weight is pretty large, right? That's what
I guess like all of these depend, like if the model is like this again is an estimate, maybe depending on like the sequence length. Like if the sequence length is larger, like this will be larger. And again, like if the model was smaller, then this would not be, then this would be much smaller.
is the one thing, but that still is the computation for values, or is it just bringing from memory still being
In the auto receive node, it's again like just bringing the entire KV cache from here to here.
you did this characterization like to figure out that this is the main challenge, like how do you do it? And usually the visibility in GPU is one of the biggest problems, right? Figuring out
Usually, okay, I don't know about GPUs, but usually there should be profiling tools. So you run a computation and there should be, I don't know like what the profile.
This is the coming because the memory was
Yeah, yeah. Yeah, so profiling tools usually give that information. I think GPUs should also have some profiling tools.
we were not able to do this. So
I see. Okay, so what we're saying is that anything that reduces this memory transfer can help us achieve latency improvement. Okay, so how can we try to reduce the total amount of like things that we are taking from HBM to the processor? So let's first look at the softmax layer, for example, right? So the eventual response is sampled from only a top K. So basically, for every token prediction, we have a probability distribution over the entire vocabulary, right? But it turns out that sampling from the entire vocabulary is not good. So what people usually do is what is called nucleus sampling. What that means is that you pick top some number, let's say 64 or something like that, and then you sample only on those 64 things according to, so you renormalize the distribution only on those 64 things, and you only sample from those 64 things, right? So this is what is called nucleus sampling or this top K sampling.
you will not know which is
Yeah, that's exactly the question. So you want to approximately, like you don't want to compute like everything and then compute the 64. You want to somehow approximately compute all the probabilities, let's say, with like which should be much faster. Like this, because this is approximate, you should be able to compute it hopefully much faster. And then you only use the softmax embeddings for those estimated top K, and then you'll be able to compute the exact probabilities much faster. So there are two aspects again. So if we can approximately compute the top K quickly in lesser amount of time compared to computing everything and then picking the top K, then you can take that approximate top K computation, and then we'll compute the probabilities only for them by using the parameters only corresponding to those particular tokens. Yeah, I think it's maybe the term is a bit more generically used. Yeah. So in this context also, this is called nucleus sampling. And the main idea is either you can have like a threshold on the probability, or you can have a top K. So, but the key point is you don't want to sample from the entire thing. You restrict yourself to many things. And also from an implementation point of view, like this is much easier because like this gives you a fixed guarantee on how many you're going to use. Whereas, yeah. Okay. Now let's look at the feedforward layer, and it turns out that even without training for sparsity, the feedforward layers have been shown to be sparse. What I mean by that, what I mean by sparse here is that the activations are sparse. So if you remember, we have feedforward layers are W2 times phi of W1x, right? So if we call this to be, let's say, y, then y will be a large vector, but it turns out to be sparse, meaning like it has fewer non-zero entries. And in this case, again, if we can approximately estimate like which of these are going to be non-zeros, then we only need to work with like those particular columns of W2, because like W2 times y will only take the linear combinations of like those particular columns, right? Again, like the goal will be to somehow identify approximately and quickly what the non-zero elements of this W1x could be, and then yeah, this is a input dependent sparsity.
Sparsity is coming because of the ReLU activation function. It is
Yeah.
throwing out the negative.
Yeah, ReLU and JLU also have the sparsity, and in particular, like if you train with sparsity, it turns out like this top k. If you train with top k in the training loop, it turns out that it even further amplifies sparsity. But even without it, it turns out that like the activation functions that we usually use, like ReLU or GeLU, they automatically lead to sparsity. Yeah. So there have been some works earlier where people have tried to train a small network to predict non-zero activations, and most of them end up suffering some amount of accuracy loss due to inexact predictions, right? Because like they directly try to predict exactly what are going to be non-zeros. So the key insight, so some of the key insights in our work, which we try to address from prior work, is that firstly, like we work with top k trained models instead of relying on natural sparsity, and it turns out that like even a small amount of top k tail patching, so even after the model has been trained, even if you continue training it with a top k in the training loop, it turns out that it can substantially amplify sparsity without losing accuracy by too much. And further, like if you are able to do something like group top k, where you don't pick single elements here, but rather like you try to identify like groups which are consecutive, which are non-zero, it turns out that this has a huge improvement in enabling like faster HBM to processor transfer compared to transferring only like single vectors. Does that make sense? So let's say you have a matrix like this, and we are saying like with sparsity, I want to transfer these vectors. So I want to use only these two vectors for the computation, right? If I want to transfer these two vectors, which are like completely in different places, then it takes some amount of time for this transfer. But if it turns out that I can transfer only a single chunk of two vectors which are adjacent, right? This turns out to be much faster compared to this.
Right. This is because of the coalesced memory access. With the memory, if all the elements are continuous, then you can quickly take the entire row of the DRAM and then basically send it. Is it because of that?
It basically is because of the way the fetch instruction is broken down, or the transfer operation is broken down into multiple instructions, and each instruction also has a startup cost. So if you are able to break it down into fewer instructions, each transferring like larger amount of memory, that's faster because like you suffer the startup cost only on one instruction. But if you break it down into multiple fetch instructions, each of them will suffer its own startup cost in addition to the transfer cost. So that's the, yeah. Right. So the point I want to highlight here is that like working with group top k seems necessary to make this efficient, because that's the thing that hardware can work efficiently with. And the second insight, this is input dependent, right? So sorry. Yeah. So what we are saying is, if you are picking like this vector, you might as well pick the next three vectors, right? And instead of having a top k over like these n different vectors, you will have a top maybe k over 4 on n over 4 groups of each with 4. And the point here is that grouping them turns out to not have accuracy loss. Maybe, yeah. These actually also depend on the hardware that you are working with, and again, like you have to like use the profiling tool to profile like how much this memory transfer is taking. If I make it like group of 4, group of 8, and usually like powers of 2 is what you would need to evaluate with, and after that, like you would get a sense of yeah. I mean, I'm just explaining the group sparsity. What I'm saying is that here, like you have n different vectors, and you might want to take. So ideally, the unstructured sparsity would be you pick k out of these n things, and they could be anywhere. Instead of this, if you can enforce it being that you have n over 4 groups, each of group size 4, and I can only pick k over 4 groups. This has much better efficiency compared to this, and in terms of accuracy, again, like it doesn't lose much. I think like, that's the main insight. So the second intuition is that the main reason that these earlier works were lossy because of these inexact predictions is because they were not able to capture all the non-zeros, because whenever you're doing some kind of approximate computation, you are bound to not get some of the correct ones. So the main insight there that we try to use is that if you know that the model is working well with a particular top k sparsity, you can use this approximate computation to identify a larger subset k prime, which can hopefully guarantee, which is more likely to have guarantee that the top k are going to be contained in this k prime, because you are choosing a larger one. So the point is, precision is not the important thing, and recall is the most important thing. Maybe that's the key insight here. So even if you are not precise, even if this k prime has like a lot of spurious things, you're not going to suffer in terms of quality. You will suffer maybe a bit in terms of latency, but that latency hit is still acceptable compared to losing quality by enforcing exactly picking the top k. Yeah, yeah, all the feed forward and softmax layers, and I'll just try to explain like the high level idea, and like the idea can be similarly applied to both the softmax and feed forward layers. So let's say our goal here is to compute the top k things of phi of z transpose x. So phi is again a element wise nonlinearity, z is a matrix, and x is a vector, right? So x is a vector, and then we want to find the rows that will give the top inner product with x, the top k rows that give the highest inner product with x, right? So in stage 1, what we do is we get an approximation of z, which is z2 times z1, right? Which is a low rank matrix. And the important point here is that the total amount of model parameters required to represent z2 and z1 is smaller than the number of parameters in z. So that is true because we will take z2 and z1 to be a low rank approximation of z, right? So a low rank approximation, like for a small enough rank, will have much fewer number of parameters compared to the matrix that we are trying to approximate. And in order to compute z transpose x, we had to transfer like the entire matrix z from HBM to the processor here. In order to compute this z2 times z1 times x, we only need to transfer like the z2 and z1 from HBM. So in terms of the amount of parameters that we are having to transfer, this will have much lesser. And once we compute this, we compute the top k prime indices corresponding to output z2, z1x, and then we on z we only look at those rows and compute the inner product with x, and then that's how we get the top k prime, which is going to contain like the top k, like again this is an empirical claim, but the top k prime that we are going to get here is going to contain like the top k of the original z times x.
Can you tell us how to come up with this low rank volume?
I mean, there could be multiple approaches. So in the kind of experiments that we did, for example, we multiply so the question will become more about training efficiency. So you already have a trained model, you want to tweak it without actually having to retrain it for a very long time. So the naive approach would be to remove z and put z1 times z, like this matrix is z1 and z2, and then train it. It turns out that this takes very long to train. So the main approach that we use, which seems to work better compared to like many of the other. So another approach could be you just take Z and then take a SVD decomposition and then use the top few things. But the one that actually seems to work best is that you keep a Z here and you put a small low rank matrix in the middle here, right? So you put a like U and V transpose in the middle here, so that V transpose X will be in a smaller dimension, Z times U will be in another smaller dimension. You freeze the entire model and you only train these U and V parameters. And the number of parameters that you're introducing here is extremely small, because this does not even depend on the vocabulary dimension. So this is usually the model dimension of the vector, and let's say this is in the order of thousands, and this is for the softmax layer, this is in the order of hundreds of thousands, right? So when we are introducing a small U matrix and V matrix here, that will be on the order of maybe 1000 cross 100 and 100, yeah, 100 cross 1000. So that's roughly like 100,000 parameters, whereas this matrix is on the order of tens of millions of parameters.
So you're gonna train to learn this Zoran, which you're gonna post multiply Z. Is that what you're gonna?
Sorry, can you repeat?
You're gonna train to figure out what is the right matrix to post multiply.
Yeah, yeah.
But then so now it's not input dependent, because now you're gonna do for all sort of input tokens, right?
No. So what I'm saying is, like this top k, you need to multiply. Okay, so all I need to figure out is this Z1 and Z2.
Right.
Once I figure out Z1 and Z2, this will be input dependent, right? Because I need to multiply an X with Z1, and then this vector I need to figure out like
decomposition is not X. That's what
this decomposition is not X dependent. Yeah, yeah. So that will not be X dependent, but like which of these will be the top inner products, that will be X dependent.
It sort of tells you that model itself is sparse and it's not trained like that, right? Because you're saying the universal sparsity there somehow, right? That your model is like Z itself should be broken down into.
Maybe you can think of it as it has like multiple different cluster centers, and maybe you're just identifying like which cluster centers, like you're basically clustering the space. Depending on the input, you are looking at the cluster centers which are most relevant to that particular. We usually take k prime to be about like 2 times k. Yeah. So the one that I just mentioned is the low rank approximation, which does require some training. We can also use a quantization based approach where like instead of using Z in the whatever quantization we usually use, we can use a much more aggressive quantization like 2-bit or 4-bit, and this actually does not require any training. And on a 1 billion parameter language model, it turns out that when we apply HiRE only on the softmax layer, we get about 1.22x speed up without any accuracy degradation. And similarly, when we apply on both the feedforward and softmax layers, we get about like 1.5x speed up on this 1 billion parameter LLM. Yeah. So let me skip these figures because mostly we have gone through them. So let me quickly move on to the second part. So how much time do I have? Okay. Right. Okay. So let me try to be quick. Okay, so we have seen this autoregressive LLM inference, right? So we first give a query and then the model produces only one token at a time, right? What we want to understand is whether we can mitigate. Okay, so whatever I said earlier was specifically for the autoregressive component because it's memory bound and not this compute bound, and we were trying to reduce the amount of memory that's being used. This is trying to attack a orthogonal question, which is, can we actually not have this autoregressive nature? Can we make it a bit more compute bound? And that's what we are trying to do here. And conceptually, if you think about it, like there are two tasks that an LLM is trying to do. It's both trying to understand what the user is asking, and then based on that understanding, it's also trying to generate a response, right? And usually in the classical NLP literature, people have thought about more of these encoder-decoder models, where an encoder is supposed to understand what the query or what the user is asking, and then a decoder is the one that's supposed to generate a response using that understanding, right? And because LLMs are decoder only architectures, which means that there is only one model which both process the prompt and then keeps on generating the response. Both of them are kind of coupled. And so the other conceptual question that we want to ask here is whether we can decouple the capacity that's really required for understanding versus generation. Right. So tandem transformers is an approach to try to answer this question. And what it does is the following. So we have, let's say, a query, right, which is described in Himalayas. So a large language model processes this and then produces query representations. In the attention layers, we have keys and values. So we have a projection layer which projects these keys and values or representations to compute keys and values that a smaller language model can directly attend to in its attention layers. And the response tokens are autoregressively generated by the small language model. So the small language model in its attention layers, only in its attention layers, it attends to the keys and values that come from this large language model and this projection layer. And then there are those, and it attends to them, and then it generates the next token. And only for this token, which has not yet been processed by the large language model, the small language, like in this step, it attends to the keys and values of this token from small language model. But for all of the past tokens, it attends keys and values that it got from the large language model. Yeah, so the two main questions that we want to ask is whether these small language models, because it's being given access to large language models representations, can the quality of this small language model be improved? So will it have higher accuracy? And second, because it is also specifically aligned to this particular model, will it be more aligned with this large language model compared to a completely independent smaller model? Does the idea make sense? Any questions? Yeah, so this is actually different from knowledge distillation. So knowledge distillation happens only during training, right? And usually knowledge distillation you would do by using teachers' logits as a target for training. Here, this happens also during inference, where like you give this as a query, and then this computes all the keys and values that this small language model can use to actually generate the response. So this is during inference time. Even, I mean, during training also, we have to train it in this way. Yeah, model size. This is autoregressive. But the point is, when we look at how the large language model is being used, it's not being used in autoregressive mode. So it has these keys and values, then this generate autoregressively, and then this processes both of these and updates its keys and values, and then small language model again goes on in autoregressive mode. So we are mitigating the autoregressive nature of the large language model, but overall, like there is still an autoregressive nature here, and it seems like some autoregressive nature is necessary if you really want to ensure that this mountain is actually conditioned on A, right? Yeah. I'll come to speculative decoding. It is different. So this can be thought of as a potential drafter that can be used within speculative decoding. Yeah. So we have some experiments on a standalone model and then also with speculative decoding. So in a large model, like the quality of this output will not be the same as the large language model, but it turns out that this is similar to some intermediate model which is between large language model and small language model. So when seen as a model, standalone model by itself, I would say that this probably gives a different trade-off curve between quality and efficiency. Like if you just look at standalone model sizes, that will give you some kind of curve as to quality and efficiency. And this gives you a different point on that quality efficiency trade-off. And the main benefit of this right now we see is more in the speculative decoding framework. I'll explain that in a bit and then yeah. So I'll just summarize this because we are short on time. But we trained this with like two different model sizes. So LLM is this bison, SLM is a gecko. So this is a much smaller model, and then we have something like an otter sized model, which lies in between like the sizes of both of these. And the overall punchline, without going into all the results right now because of lack of time, is that if we can train a tandem of this bison and gecko, which is similar in quality to this otter model, but is slightly faster compared to the otter model. So this when it is used in a standalone mode. But I think let me quickly jump to the setting where we want to use this without actually worrying about accuracy. And this is where this framework called speculative decoding comes into picture. So the main idea in speculative decoding is that we use a small model to generate these tokens autoregressively, right? And so this is autoregressive generation here. And once we generate like these 4 tokens, we use a primary model to and give this 4 tokens that have been generated as input, right? And once we give them as input, then this also produces tokens all at once by using again masking similar to how it was trained. And then we see that the output is not consistent with the input at this point. So here the output is saying is, and the small model has generated R, right? Then we say that the small model generated a wrong output. So we go back and condition on is, and then we start the generation of the small model from that point onwards. So in 4 autoregressive steps of the small model and 1 step of the primary model, we're able to generate about 3 tokens, right? And as long as the total time taken by 4 autoregressive steps of the small model and 1 step of the large model is still less than 3 autoregressive steps of the large model, we are going to, this is going to be faster, right? And the hope is we will be able to produce, like the small model will be able to produce many tokens which are going to be accepted by the primary model, which can further, like which can enhance the efficacy of speculative decoding. And yeah, so this is called backtracking. So R was not equal to is. So if the small model had actually generated is, and then like there was a mistake only somewhere here, then we would have gotten like almost 5 tokens in this one step, right? So if you have less backtracking, we get more speed up. And the way we can try to get less backtracking using tandem transformers is that instead of using a standalone model as the secondary model, we can use the primary model because it has already processed all the tokens that have been generated so far. We can use them to compute the KV cache of the secondary model using these projection layers. And what this means is that the quality of the secondary model will be much better compared to the quality of a standalone secondary model would have been. And which means that the amount of backtracking is going to be smaller. And this overall improves the effectiveness of speculative decoding. Sorry, this is.
Just the recurrent on the right side. It's looking like the one.
I guess it's not. It's a transformer. No, I mean it's a transformer, but it's just the autoregressive nature is making it look like recurrent.
You're
like,
still passing the information from the first to second, like it is almost behaving like a recurrent neural network, right?
I mean, you are passing like the KV cache of all of the past tokens from here to here.
The KV cache from the first small model is passed to the second one, or?
Yeah, I mean, all of these are the exactly same model. Like the model weights are exactly the same. Maybe let's take this offline. I think it's maybe just like the picture might not be very clear in terms of exactly what's happening, but yeah. Okay, so hopefully I have okay. Let me just conclude, like because of the time. I think like I have given like the most important idea, which is that speculative decoding, like by itself, uses like a standalone small model for doing this autoregressive. It's called a drafter, and it predicts a draft of like the next 4 or 5 tokens. If it were a standalone model, it would have had some quality and some amount of backtracking. Because we are enabling the small model to attend to the keys and values that were generated by the primary model, which is a bigger model, the drafter model will now improve in its quality by being able to attend to the keys and values from the primary model, which means that there will be less backtracking in speculative decoding and we will get more speedups. Yeah, so let me just conclude. Hopefully, like I've convinced you that inference latency is a big bottleneck and we are still very far from being like efficient. And this is especially critical given the kind of models that we are seeing right now with like very large response lengths, like the thinking models and like O1, O3 and so on. And in this talk, we particularly presented like two approaches. So one is called HiRE, which is specifically for efficient top K, which gets about like 1.5x speed up over like a dense 1B model, and applies to all the layers. And some of the directions that we could think about in this context is to exploit top K overlap across like multiple tokens in a batch, and how we can like make this more effective even for like very large batch sizes. The second approach that I presented is tandem transformers, which is specifically designed to mitigate autoregressive component. Specifically, when we use this inside of speculative decoding, compared to like just distilled but independent models, we get about like 1.11 to 1.17x speed up. And there are also other variants of tandem, which could be using an LLM for generating a plan, and then maybe only a small model to actually do the autoregressive decoding of the sampling of the next token. And tandem as an architecture seems to be pretty powerful. So it will also be interesting to understand whether tandem transformers can be thought of as an alternative to LoRa for fine tuning, where we have task specific, maybe primary models or secondary models, which attend to like a large model for improving their quality and getting general reasoning, but can still be specialized into different tasks. Okay, I'll stop here.
Thank you, Dr. Praneeth, for an informative talk, and thank you everyone for attending. Do we have more questions from the audience? Okay. Thank you. We have arranged refreshments in the coffee hut. Please have them. Continue our conversations there.